Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So let's continue our class with the parallel hardware. So let's see now the classification of parallel hardware. It depends on instruction two characteristic, which is the instructions and data. So something like multiple input, multiple output, and depends on the how many instruction and how many data. Then you have single instruction, single data, single instruction, multiple data, multiple instruction, single data, and multiple instruction, multiple data. Okay, so this is least used architecture, but the others is has been used architecture. Okay, so the single instruction, this is based on the Flynn's taxonomy. Okay, the single instruction, single data is the classic von Neumann architectures. Okay, in which you have CPU, and then we have processor, we have memory, and we have I/O and so on. Okay, then single instruction, multiple data, you are the instruction is applied to multiple data. So for example, here the GPU is one of the example of SIMD. Okay, sometimes also the next one, GPUs become hybrid because they can run different instructions also for different data. But the most known example for this one, multiple instruction, multiple data, is the multi-core machine. Okay, in which you can have run different instruction in different machine, and then you can also operate different data on different cores. Okay. And yeah, so the next one, multiple instruction, single data. So this one is less common, but found in the pipeline architectures. Remember that the one that we discussed earlier. Okay, we have the pipeline architectures. Okay. Yeah, so this is the visualization of Flynn's taxonomy. You have the data, okay, and you have the instruction, okay, and this is single, this is multiple. So you can see that this is the processing element. Instruction, one data, okay, MISD. So this is again for systolic array or pipeline architecture. So you have one data and you have multiple instruction. Okay, SIMD, you have multiple data and you have one instruction. MIMD, you have multiple instruction operating on multiple data. Okay, so let's see how the modern CPU and GPU exploit the different level of parallelisms. So for example, multiple cores is using the MIMD parallelism, but because you have multiple cores which can run multiple instruction and operate on multiple data. Okay, and this one of course can execute threads asynchronously. So different thread for different processor, for example, independently. It does not depend on the on other threads on other cores. Okay, so this work independence. Okay, so you can put, for example, Microsoft Word program in core number 1 and PowerPoint core number 2, for example. Okay, it can run independently without interacting to each other. So asynchronous also. Okay, and then we have also vector units, which like this is like a single instruction multiple data. So instead of working on one element, you are working on a vector, okay, or an array, okay, an array of data. Okay, so the vector unit can execute vector instruction. So you have another one which is vector instruction, okay, for the vector data on a number of data items simultaneously. For example, you have 500-bit vector unit can perform an addition of 16 pairs of single percent floating point numbers in parallel. Okay. Okay, so then you have instruction level parallelism. So the current process also further exploit instruction level parallelism. Like an Intel, you have hyper-threading, for example. Okay, so it looks like you can see also in the task manager, if you go open the Windows, you have physical core. Okay, and then you have logical core. Okay, logical core. Okay, because one core can run two threads at the same time for hyper threading. And then so that's why it's one physical core. It looks like you have two cores, okay, at the same time. Okay. Okay, now let's see one by one. The SIMD architecture exploit data parallelism. So whenever you can divide the data, you can operate independently. Then you can use SIMD architecture. So one example is like a GPU, as I mentioned earlier. So you have we have so many pixels in one image or one video, for example, and then you calculate the shade for 1 pixel, okay, until the end of the pixel. Using the same instruction, you can calculate the shade, for example. Okay. So they only require a single or centralized control unit as the controller of the many processing elements or LUs, okay, to dispatch instruction. And then the instruction is broadcast from the control unit to the LUs, and each LU either applies the instruction to the current data item or it is idle. Okay, so depends whether you have enough data or not. Okay, so let's see here. Suppose you want to carry out a factor addition. Okay, there are two arrays of x and y. Okay, each with n elements. Okay, and we want to add the elements of y to element of x. Okay, so xi equal to xi plus yi. Okay, so you have the addition of each element. Okay, so you have here the n. Okay, and data items and LUs. Okay, so you can run it in parallel. Okay, so the same instruction but multiple data. You can see here you can have multiple data. Okay. So now let's see the practical situation. Of course, you can if you cannot have, for example, you have n equal to 100 elements. For example, you have also processor for 100. Okay, m equal to 100 as well. Okay, processing element of LU of 100 as well. Normally you have smaller LU. Okay, so you need to divide the work. Okay, you cannot run it one go, but you need to divide the work so that all can be calculated using several steps. Okay, but still a faster step compared to the if you don't use the SIMD. Okay, so for example, we have 4 LUs. Okay, only 4 LUs. Okay, percent elements. It's like what you call the M1 processors has, for example, 8 core CPU and 8 core GPUs. Okay, so it's the same thing, but in our case here, m equal to 4 LUs, and we have only 15 data. Okay, not 16 but 15 data. So what we do, we can have several rounds. So we can divide from, you have 0 to 14. Okay, you can have 0 to 14 element, so you can divide 1, 2, 3, 4. Okay, so the first one, round 1 is 0 to x3, round 2 x4 to x7, round 3 x8 to x11, round 4 x12 to x14. You don't have 15. Okay, so this LU number 4 will be idle. Okay, in round 4. That's okay. Okay, so because we still have faster calculation. Okay, because instead of doing 15 times, if you can translate into, let's say, 15 nanoseconds, okay, you only need to run for 4 nanoseconds. Okay, so 4 times faster. Okay, almost 4 times faster. Okay, but the requirement of that all LU execute the same instruction or remain idle, or this is the key point here, can degrade the overall performance. Okay, because the idle one we need to take care also. Okay, we need to count that into the parallel time. Okay, so for example, in this setting, we must load each element of y into data path and determine that it is positive. So if you have some condition like this, so only the one that has y positive, then you do calculation. Otherwise, the other one is idle. Okay, so that idle is not useful, but you still need to run it in one instruction. Okay, so this condition make the parallel time worse. Okay, or parallel CPU utilization or LU utilization is not fully utilized. Okay, or some have the idle. Okay. So in classic design, they must also operate synchronously. So each LU must wait for the next instruction to be broadcast before proceeding. Means that before you move on to round 2, all the LU need to finish the respected elements. Okay, so they need to wait. Okay, if you have 4 LU, one going first, another going later, like this. Okay, they need to wait, start until the end. Okay, so you can see also there is some overhead. Okay, there's some overhead. Okay, instead of you using 1 nanosecond only, then you have maybe 1.4 nanosecond and so on. Okay, so this is also wastage of time. Okay, so the LU have no instruction storage, so it cannot delay execution of an instruction by storing it for later instruction. Okay, so this SIMD is efficient for large data parallel problems, but not other type of more complex parallel problem in which you have some conditions. Okay, and the data is not independent. Okay, so it's dependent on the previous element, for example. Okay, so yeah, so this is the drawback of SIMD. Okay, the next one of the example is vector processors. Okay. The key characteristic is the ability to operate on arrays of vectors of data rather than individual data elements or scalars. Okay. So of course, the vector processor has vector registers because you need to you need to save the data from 4 to 256 64-bit elements. Okay, so depends on the vector can range from 4. Okay, so means that you have 4 64-bit, 2 64-bit, 3 and 4, or until 256 elements. Okay, depends on your budget for the vector processors. Okay. And then they have factorized and pipeline functional units. Okay, and then they have also vector instruction, operate on vectors and data, and interleave memory so that you can provide faster memory access. Is by having the interleave memory, you can distribute element of vector across multiple banks. Okay, so for example, you have 1, 2, 3, 4, and you have 2 banks of memory. Okay, you can allocate this one and 2, 3 to here, 4 to here. Okay, so that you can work at the same 1 and 2 can have at the same time, and 3 and 4 can have can be read or write at the same time. Okay, so it can be load or store at the same time. Okay, and they have also strided memory access and hardware scatter getter. So the strided means you can have, if you have 0, then this is 9, this is 10. Okay, you can access directly on the strided configuration. Okay, 0, 10, 20, and continue. Okay, you can you have the, if you have fixed intervals. Okay, so you have the strided. Okay, or you can have also scatter and gather. So you scatter the value and gather at irregular interval, gather back the value at one intervals. Okay. So the pros for vector processor is very fast because you are operating on the vectors rather than individual elements. Very easy to use. So provided that it can be factorized and can be mostly what you call, it's not depend from the other data. Okay, and then factorizing compilers are good at identifying code that can be factorized. Okay, now you have the compilers that is good to when you implement in the vector processor, then it can identify the code that can be factorized. Okay. Compiler also can provide information about the code that cannot be factorized, so that you can evaluate the code, you can rewrite the code so it can be factorized. Okay, you have very high memory bandwidth. You can have interleave, so like twice. If you have 2 banks memory interleave, then it looks like you have twice of the data rate. Okay, and use every item in cache line. It is fully used. So then the negative or the disadvantage, they do not handle irregular data. Remember that you need to have factorized and independent data. Otherwise, it will slow down the processing time. Okay. And this one have a very finite limit to the ability to handle ever larger problems. Okay, so the current generation scales by increasing the number of vector processor, not the vector length. So you cannot have, for example, more previously what we have here, 4 to 256. Okay, 4 to 256 elements vectors. Okay, so the scalability achieved by increasing more the processing element. Okay, processing element, not the length of the vector. Okay, yeah, so not the length of the vector, but the processing element. Okay, the next one, the example of assembly system, this very popular, which is the graphic processing unit. Yeah, so for example, here you have RTX 3090s and Radeon's processor 590, I think. Yeah, so this is an example of SIMD system, but this one cannot be independent. They still need the CPU for as the controller, okay, as the controller for managing all the operation in the CPU as well as on the GPU. Okay. So the GPU pipelines convert the internal representation into an array of pixels, like of vectors, and can be sent to a computer screen. So you have several stage of this pipeline called the shader function, which is programmable, and typically just a few lines of C code. Okay, and this is also implicitly parallel, since they can be applied to multiple elements in the graphic stream. So as I mentioned earlier, you have multiple pixels, so you can apply for multiple pixels at once. Okay, you can have in a row, another rows, and for example. Okay. The current generation of GPU use SIMD parallelism by including a large number of values on each GPU processing cores. So processing a single image can require very large amount of data. So the GPU needs to maintain a very high rate of data movement. So as if you follows, you have the CPU here, I represent by cores or C, and you have memory, okay, connected to the I/O bus, to the bus, okay, and then you have GPU. The GPU has video memory as well, okay, and then you have the GPU core here, okay. So the single image you need to read, of course, you need to read from here. Sometimes you can bypass also to video memory, okay, but normally you load first into the main memory and then you copy to the video memory, okay. So the GPU rely heavily on hardware multi-threading, okay, not software multi-threading, but hardware multi-threading. So by design, it can run multiple threads at once, okay. Okay, so the GPUs are not pure SIMD system because it can run not purely SIMD, not purely as MIMD. So you can have what you call different. If you have, for example, 256 cores of GPU, one can be run on another data, one can run in another data for different instruction. Okay, so it's hybrid system. Okay. Okay. Then the next one, we move on to MIMD system, which support multiple simultaneous instruction streams operating on multiple data streams. Okay, so you have multiple instruction and you have multiple data. Okay. Unlike SIMD need to be synchronous. Okay, so you need to wait first until all has finished the processing. Okay, so for example, you are going row by row. You need to finish all the processing row by row first. If you have only 4 cores, for example, they have some overhead. So you need to wait until all the 4 cores finish calculation. Then you can move to the next row. Okay, or next element. Okay, okay, and move on. So this is synchronous. Okay. But the MIMD system are asynchronous, so it doesn't matter. Okay, you can run multiple program at once. Okay, so this is core number 1, core number 2, core number 1, core number 2, and this is process 1, process 2, process 3. Okay, and then process can run independent. Okay, so this is on core number 1, this is core number 2, this is on core number 1, for example, if you have dual core. So this is asynchronous. Okay, depends. It's not dependent. Okay, the program number 2 here does not depend on program number 3 to finish. They can run at the same time. We can do overlapping. Okay, but program 1 and 3 will be synchronous. Okay, because they are on the same cores. Okay. So in many embedded systems, there is no global clock, and there may be no relation between the system time or two different processors. Okay, and there are two principal type of MIMD system, which is shared memory system and distributed memory system. Okay, so shared memory, you have CPU, and interconnect, you have the memory here. Okay, we will discuss this one in a moment. Okay, and then CPU interconnect to the memory and CPU to the memory and so on. Okay, from here also you have, so you can see this is shared memory. Okay, so if you put the matrix A here, it can be read or write by CPU number 1, CPU number 3, number 2, number 3, or number N. Okay, they can write this one. Okay, they can access and write this variable. Of course, you can also define private variables. So for example, if you define some temporary variables, okay, and for CPU number 1 only, so the other CPU cannot access to this one, cannot access or write this one. Okay. Okay, so distributed memory, as the name implies, by default, it is not shared. So in order to share, you need to pass to send and receive. So this is the two basic operation on a distributed memory, which is message passing interface. Okay, the program model is message passing interface. Okay, you have PC number 1, PC number 2, PC number 3, PC number N. Okay, so you have CPU memory. So for example, if you have what you call array of A here, okay, the PC number 2 cannot read because this is on different memory. Okay, so you can send to CPU number 2, for example, and then CPU PC2 will receive A here. Okay, if you need A to be on all memory on the cluster, so this is cluster computing, for example, on the cluster, so you can broadcast matrix A to all the PCs, okay, in a cluster. Okay, so this is the different type. There are two types of MIMD system, which is shared memory and distributed memory. Of course, each own CPU can operate on multiple instruction, multiple data. The same case with this one. So you have multiple instruction and multiple data. Okay. So in a shared memory system, a collection of autonomous processors, autonomous because it can work on its own, is connected to memory system via an interconnection network, and each processor can access each memory location. Okay, there are two types later on, UMA and NUMA, the interconnection network, uniform memory access. Okay, and the other one is non-uniform memory access. Okay. So the cache, now multi-cores have level 1, level 2, and shared LT cache. Okay, shared LT cache. Okay, so depend on memory interconnection, there are two shared memory type, which is uniform, as the name implies. This is uniform, so every core has the same access to the memory. Okay, or you have non-uniform, so only selected cores can have access to the selected memories. Okay. So this is, for example, UMA or Uniform Memory Access System. You have chip number 1, core 1, core 2, chip 2, core 1, core 2. So this is an example of SMP, symmetric multiprocessor. This is on socket number 1. Okay, this is on socket number 2. And each socket also has 2 cores here. Okay, so you have 2 sockets, and each socket has 2 cores. So altogether you have 4 cores. Okay. So in here, time to access in UMA, the time to access all the memory location will be the same for all the cores, whether this from chip 1 or for chip 2 or core 1, core 2 on each chip, it will be the same. Okay, and this is easier to program because the programmer does not need to worry about different access time. Okay, for different memory location. So it doesn't matter you put it here or you put it here. Okay, the same access time. Okay, different memory, different chip. Okay, different core, it has the same access time. Okay, while for NUMA multi-core system, you have different architecture here. Okay, a location of a core is directly connected to can be accessed faster than a location that must be accessed through another chip. So for example here, this A, if accessed by this one, is faster compared to you if you want to access by core number 2 here. Okay, you want to access, you need to connect the chip 1, get the permission, and then they go here. Okay, so this one will be faster compared to this one will be slower. Okay, vice versa. Okay, if you have B here, and then this core number 1 will have slower access compared to core number 2 here. Okay. Okay, so yeah, then we move on to MIMD. The most widely available distributed memory system are called cluster computing. So you connected several PCs using interconnection network. For example, you have LAN, Ethernet LAN, for example, local area network. Okay, you connected to the switch, Ethernet switch. Then you can see that it can be what you call connected to form a cluster. Okay. So cluster is collection of commodity system. So it's not special hardware, but you can buy it. Okay, you can this is a commercial system. You can buy off the shelf. Okay, and connected by a commodity internet connection network, for example, Ethernet. Okay, there are some proprietary system as well. Like last time we have MyRenet, but most of the cluster computing use the commodity interconnection network like Ethernet. Okay, of course, when you say Ethernet, you can also connect it using the Wi-Fi and so on. Okay. So node of cluster are individual computation unit joined by a communication network. Okay, so for example here I have yeah, so I have an example of MIMD system, which is this one. I can see, yeah, you can see this one. You can see it in my video. Yeah. So yeah, so this is, you have Raspberry Pi and then you have Raspberry Pi head. Okay, this is forming a cluster. So this is cluster head. Okay, so you can see I have four Raspberry Pi zeros. Okay, as a slave, and one master Raspberry Pi 2 as a master, and then four slave. Okay, so this is an example of hardware. When you put matrix A in one of the memory here, okay, it cannot be read by the others Raspberry Pi. Okay, so you need to send what you call officially. I mean, you need to send the message to broadcast the memory. Okay, yeah, so that the others can read. Okay, so the node of cluster are individual computation unit joined by a communication network. Okay, so this one node, so you have node 0, node 1, node 2, node n-1, okay, and so on. Okay, so nowadays it's usually understood that a cluster will have shared memory node as well. So this become a hybrid system, means that even in one node, okay, you have multiple core there. You have 2 cores, 4 cores, and so on. And then you connected to the network. So you have shared memory in here. Okay, each node you have shared memory, and then you do hybrid. Okay, so for programming, okay, for programming, normally they use the simple, because it will be difficult to program one in shared memory and one in the distributed memory. So normally they put here, treated as what you call message passing interface, means although you have also in the shared memory system here, but you treat it for different process, mean you need to send the data. Okay, you need to send the data. Okay. Okay, so this is an example of cloud computing, also the form of MIMD, okay, distributed memory system. Okay, so the interconnection network. Yeah, so now we move on. We have the shared memory has interconnection. The MIMD also has the interconnection. Okay. Okay, so the interconnect plays a decisive role in the performance of both distributed and shared memory, because if that is become the bottlenecks, okay, yeah, it will slow down the computation. Okay, so even if the processor and memory have virtual unlimited performance, a slow interconnect will seriously degrade the overall performance. So it's something like this. Okay, you have the bottleneck. You have big power but small road here. Okay, big memory, for example. Okay, so this one become the bottleneck. Okay, and it will degrade the overall performance. Okay, because from here you need to queue. Okay, you need to queue here. You need to queue. You cannot run multiple data or multiple process. You need to queue one by one. Okay. Okay, so now let's move on. We have two categories of interconnection network, which is shared memory interconnects. The example is bus. This is the simplest one, and the next one is cross bars. Okay, more advanced. Okay, but also more expensive. Okay, because there are some limitation on the buses here. And then you have distributed memory interconnects, which have direct and indirect interconnect. Okay, so let's see one by one. Okay, for shared memory interconnect, we have the bus interconnects. So this is a collection of parallel communication wires together with some hardware that control access to the bus. Okay, so if you have CPU here and you have memory here, CPU1, CPU2. So you have memory here. So all connected to the same bus. Okay, so you have 1, 2, 3, for example, 4, for example. Okay, so all connected to the same bus. Okay, all connected to the same bus. Okay, you have 64-bit line, then you have 64-bit of parallel bus like this. Okay, memory also the same. You need to connect to the 4 bus like this. Okay. So communication wire are shared by the device that are connected to it. So let's see what happens if core 1 want to access the memory, core 2 want to access the memory. So they need to wait. Okay. As the number of devices connected to the bus increase, contention for use of the bus increase and performance will be decreased because the waiting time will be longer. Okay. So this is only 2. What happens if you have 4 cores? What happens if you have 16 cores? Okay. What happens if you have more device? You have GPU, you have many IO, you have USB connected. Okay, so that will slow down it to become the bottlenecks. Okay, then we have the crossbar or we have switch interconnects. So we use the switch to control the routing of data among the connected device. So for example, you have crossbar which allows simultaneous communication among different devices. So you can C1 can connect it directly to memory, C2 can connect directly to memory. Okay, it's faster than buses, but the cost of the switch and links is relatively high. So again, the trade-off between the performance and the price. Okay. So this is a cross-bar switch connecting 4 processors, PI and 4 memory modules. So for example, we have 4 processors and 4 memory modules, M1 to M4. Okay, so this is the 2 configuration of the internal switch. So each one here, it can be like this or can be like this. Okay, so let's see here. This is the simultaneous memory access by the processor. So you can see here P1 access directly M4, P2 you can follow here, P2 access directly and M3, P3 access M1, P4 access M2. So you can see you have different access here. P1 go to M4, P2 just follow the line here. Okay, access M3, P3 access M1, and P4 access M2. So you can see they can access at the same time. If you are using bus, then you need to wait. Okay, you need to wait P1 until the bus is finished. Can get to M4. Okay, and if finished, then go M3. So in a way, if you have something like this, okay, it means that all processor requires different memory, in different location of memory, then this one can be 4 times faster. Okay. Okay, so this is the crossbar. This is so this is the 2 configuration. So with this switch and at least as many memory modules as processors, there will only be a conflict between 2 cores attempting to access memory if the 2 cores attempt to simultaneously access the same memory module. So if P1 access M4 and P2 want to access also M4, then P2 need to wait until P1 has finished or vice versa. Okay. So the crossbars allow simultaneous communication among different devices, so they are much faster, but the cost is relatively high. Okay, so there's 2 types: the bus and crossbar. So now let's move on to distributed. So let's move on now to distributed memory interconnects. It's often divided into 2 groups, so direct interconnects and then indirect interconnects. So indirect more like crossbar, direct more like bus. Okay, so switch may not be directly connected to a processor, so you need to have several hop. Okay, several hop. Okay, so you need to jump from one node to another node, then you can get the data. Okay. So direct interconnect, each switch is directly connected to a processor's memory pair, and the switch are connected to each other. So for example, ring and 2D toroidal mesh. Okay. So one of the simplest measure of the power of direct interconnect is the number of links. So you can see the number of links. How many? Each node for ring here, you have three links. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So on the toroidal mesh, so you have a mesh here. You can see every node here connected to yeah, 1, 2, 3, 4, 5. Okay, then you can connect to the other one. Okay, 1, 2, 3, 4, 5. Okay, for one node. Okay, so this is for each link. Okay. Okay, so yeah, so you can't only switch to switch links, as the speed of process to switch link will be vary. So a ring is superior to simple bus since it allow multiple simultaneous communication. So P1 can run to P2 and P3 can run to P4 and other things. The next one is toroidal mesh, but it is more expensive than the ring because the switch are more complex. You can see here. It must support 5 links instead of 3. So you can see this is 5 links. Okay, 1, 2, 3, 4, 5. Okay, so if there are P processors, the number of links is 3P in toroidal mesh. So if you have, for example, this is 3 processor. So this is the processor. Okay, and this is represent switch. Okay. So here you have 2P. Okay, so yeah, because the number of links is 3P in toroidal. Okay, 3P, and while it's only 2P in a ring. Okay. Okay, so one measure of number of simultaneous communication or connectivity is bisection width, or you can say this is the connected to the latency. So how long does it take to send the data from the farthest nodes? Okay, so how many simultaneous communication can take place across the divide between the half? So for example, in figure A here, if we have divided a ring with 8 nodes, so we have 8 nodes, 1, 2, 3, 4. Remember that this one represent the processors, and B, and the others represent the link. Okay, so in here you can have only 2 communication can take place between the half, 1 and 2. Okay, the others need to wait. Okay, if we in figure B, if we have divided the nodes into 2 parts, okay, like this, A B A B. Okay, we can have 4 simultaneous connection, 1, 2, 1, and then 2, 3, 4, for example, 4 simultaneous connection. Okay, but the bisection width is supposed to give a worst case. So in this case, the bisection width here is 2, still 2 here. Okay, not 4. Okay, because we are talking about the latency, or the worst case. Okay, for sending the data or for accessing the data between the farthest part of the nodes. Okay. Okay, so then we have also toroidal mesh. Okay, so toroidal mesh here we have the wrap around. So this is wrap around, jumping from the first node until the last node here. Okay, so if you have square 2D toroidal mesh with P equal to Q square, okay, Q is even, then you can split the node into 2 halves by removing the middle horizontals link and the wrap around horizontal link. Okay, so remove this one. Okay, and see the middle horizontal links and wrap around horizontal link. Okay, so the bisection width is at most 2Q, or in our case, if P equal to 16, so your processor is 16 here, you have 16 processors. Okay, so then you have 8. Okay, the bisection width here is 8, so means that you can have 8 simultaneous connection in one go. Okay. Okay, so the bisection width here is 2 square root of 4. Okay, you have 16 processors, then 2 square root of 16, 8. If you have 32 processor, the next one is 64, for example. Okay, 64 processor at once. So you have 2 times 8, we have 16. Okay, the bisection width is 16. Okay. Okay, now we come across the definition of bandwidth, bisection bandwidth. So as I mentioned earlier, the bandwidth is the rate at which a link can transmit the data. So how many that you can transmit in one go. So usually given in megabits or megabytes per second. Bisection bandwidth is the measure of network quality. So you can see we have the worst case scenario. Okay, similar to bisection width here. Instead of counting the number of links joining the hub, it sums the bandwidth of the link. Okay, so for example, the links in a ring have a bandwidth of 1 billion bit per second, 1 billion bit per second. Then the bisection bandwidth of the ring will be 2 billion bits per second or 2 megabits per second. Okay. Okay, what about the fully connected network? So the ideal direct interconnect is a fully connected network in which each switch is directly connected to every other switch. Okay, so you can see here, if you have 6 processor, each processor need to have 1, 2, 3, 4, 5 n minus 1 connection. Okay, not connected to it. There's no connection to itself. Okay, no need to have connection to itself. Okay, so you have if you have, for example, 32 processors, then you need to have 32 minus 1 or 31 links. Okay, so this is impractical. It's difficult to design the hardware like that. Okay, and the bisection bandwidth here is 9. Okay, but this is again impractical because each switch must be capable of connecting to P links. Okay, so this is just only theoretical best possible. Okay, but it's not numerous difficult to implement. Okay, unless if the number of nodes is smaller, like 4, even the 4 also you have at least 3. Okay, 1, 2, 3 connection. Okay. So then we have another types, which is the hypercube, is highly connected direct interconnect that has been used in actual system. So hypercube are built inductively, one-dimensional hypercubes with 2 processors, two-dimensional hypercube by joining corresponding switches like this two-dimensional, and three-dimensional hypercube is not like fully connected, so you just connect to forming the 2D, 3D, and so on. Okay. So hypercube of dimension D, 1 dimension, 2 dimension, 3 dimension has P equal to 2 times 2D nodes. Okay. For example, P here 2 to the power of 1. This is D equal to 1. So you have 2 processor. Okay. This one maximum will be 2 to the power of 2, 4 processor, and this is 2 to the power of 3. This is 8 processor. Yeah, 1, 2, 3, 4, 5, 6, 8. Okay, so the bisection width of hypercube is half. Okay, number of P over 2. So just see here, bisection width. Of course, you need to cut like this. Okay, so you have P over 2. So it has more connectivity than a ring or toroidal mesh, but the switch must be more powerful since they must support this wire. They have many wires there. Okay, while the mesh switch requires only 5 wires. Okay. Then we have beside direct connect, we have also indirect interconnects. This is provide an alternative to direct interconnects. For example, you have crossbar, okay, and omega network. So in indirect interconnect, the switch may not be directly connected to a processor. So they are often shown with unidirectional links and a collection of processors. Each has an outgoing and incoming link. So again, this box here is processor 1, 2, 3, 4. So maybe you have switching network and then you connected to N. Okay, connected to other memory and so on. Okay, so this is a generic indirect network. Okay, so for example, crossbar similar like this one. You can have a cross like this. Okay, or you can connect like this, or you can have a cross like this. Okay. Okay, the similar like crossbar for the shared memory. Okay. Yeah, so you have here crossbar interconnect for distributed memory. The bisection width is P. Okay, the bisection width is the number of processors. Okay, because you can connect. You have 4 here. You can connect with the 4. Okay. So in Omega network, the switch are 2 by 2 crossbar. So this to reduce the number of switch. Okay, there are communication that cannot occur simultaneously because you reduce the number of switch here. Okay, so you can see like this. So for example, if you have 0, 1, 2, 3, 4, 5, 6, 7, if processor 0 send a message to processor 6 like this into here, then processor 1, this one, cannot simultaneously send a message to processor 7. Okay, because they have different things. They have shared the same switch here. Okay, and the Omega network is less expensive than the crossbar. Okay, because the Omega network use half P log 2 P of the 2 times 2 crossbar switch. So it used to total 2P log 2P switch, while the crossbar use P square. Okay, so let's see if you have 8 processors. Okay, so you have 2 times 8 log 2 8. Okay, so you have 16 times 2, so you have 32. Okay, but if you are using crossbar, you have 8 square, which is 64. Okay, and the bisection bandwidth is P over 2. Okay, less than, because this is P, because you don't share. This is P over 2. If you share 3, then P over 3. Okay. Okay, now let's move on to latency and bandwidth. So anytime data is transmitted, we are interested in how long it will take for the data to reach its destination. So if you have the sender, you have receiver, you want to know how long it is. So there are two things here, which is the latency, okay, how long, or the overhead, okay, and the bandwidth, okay, the bandwidth, okay. So for example, here data transmission between the memory and cache and register, hard disk and memory, or between two nodes in distributed memory system, okay. So the latency is the time that elapsed between the source beginning to transmit the data and the destination starting to receive the first byte. Okay, so this is the latency. Okay, from the starting, always normally always the same, and then after that you take care of the bandwidth. So the rate at which the destination receive the data after it has started to receive the first byte. Okay, latency, then the bandwidth. Okay. So you have here the message transmission time is L, and N is the length of the message here divided by the bandwidth, okay, byte per seconds, okay. So when you put here L, it will be in seconds, okay, plus message in byte divide byte per seconds, okay. So you have the dimension of seconds, okay. So this is something like overhead. And if you have bigger bandwidth, you can make smaller this part only. Okay, so you need, if you want to faster communication, you need to reduce the latency and increase the bandwidth. Okay, so reduce the latency and increase the bandwidth. Okay. Okay, let's move on. This is the last part of this chapter. Let's see about now after interconnection. Now we have the cache coherence. So the CPU cache are managed by system hardware. Okay, the CPU cache are managed by system hardware, especially the MMU, memory management unit, and programmers have no direct control over cache and when they get updated. Okay, so this is not transparent to the programmer. Okay, because programmers have no direct control. So suppose we have a shared memory system with 2 cores and 2 cache. Okay, so you have here 2 cores, okay, and 2 cache 0, cache 1. As long as the 2 cores only read shared data, there's no problem. See that the problem here, whenever you have write, okay, when you have write, then you have you have started, when you updated the data, then you start to have a problem. Okay, which one to update, how to update, okay, when to update. Okay, so for example, here you have x equal to is a shared variables. Okay, so you have x here, which is in the memory. This is memory. Is the shared variables means that it can be read or write for core number 0 or core number 1 and core number 2. Okay, core number 0, core number 1. Okay, and why not is private and owned by core number 0. So this is shared. Okay, this is private core number 0 by core number 0. Y1 and Z1 is private. Private means core number 0 cannot access this Y1 and Z1. Okay. So suppose the following cache coherence means the coherency of the cache. Okay. Suppose the following instructions are executed. So you have Y0 equal to X. So Y0 is core number 0s and X equal to 7. So the problem is here when you write the write here, you have the writing. Okay. So core number 1 is Y1 3 times X. So it depends. Okay, and now it's depend. So Y1 here, which is private to core number 1, 3 times X. Okay, and the next one is the terminal information X, and Z1 here is 4 times X. So here is the problem is which X. Okay, which X is this X or the earlier X equal to 2. So here will be X equal to 2 or X equal to 7, which one? Okay, because the core number 0 has updated, has right here. Okay, so why not will eventually get the value of 2 because still get 2 here. Y1 will eventually get the value of 6 because 3 times 2 is 6 here. Okay, however, it is not so clear what value Z1 will get. Is it 4 times 7, 28, because you have updated this one, or this is still the odd one, 4 times 2, 8. Okay, I repeat, because this is x equal to 2 or x equal to 7 here. Which one? Okay, depends. Because if you put the catch here, catch is x, or you put also catch here, this one catch is still 2, this one catch already 7 because you have written there. Okay, it's not yet propagated to the main memory. Okay. So it might first appear that since 0 update x to 7 before the assignment to Z1, Z1 will get the value of 7, 28. However, at time 0, x is in the cache of core 1, for example. Okay. At time 0, x in the cache of core 1. Okay. So for example, x here is in the cache of core 1. So unless for some reason x is extracted from core 0 cache and then reloaded into core 1 cache, it actually appears that the original value of x equal to may be used, and Z1 will get the value of 8. Okay, so you can see the problem happens when you have updated the system. So you need to propagate, okay, the value, new value, so that if you updated here, you need to propagate in here 7 and propagate in here as well. Okay, so you need to have a cache coherency. Okay. Yeah, so this one also, whether we are using write through means or write back policy. Write through means we update instantaneously. So whenever the cache update here, it will need to update here and as well in here. Or we just have or mark as dirty write back policies. Okay. If it is using a write through policy, the memory will be updated by the assignment x equal to 7 directly. However, this will have no effect on the value in the cache of core 1. Okay, with core number 1 cache, the x value still will be 2. Okay, so if the system is using a write back policy, the new value of x in the cache of core 0 probably will not even be available to core number 1 when it updates Z1. Okay, because it still mark it as dirty, but not write it yet in the main memory. Okay, and then the programmer does not have a direct control over when the cache are updated, so the program cannot execute this apparently innocent statement and know what will be stored in Z1. Okay, so the cache described for single process system provide no mechanism for ensuring that when the cache of multiple processors are stored the same variable and update by one processor to the cache variable is seen by the other processors. So we have a cache coherence problems. Okay. So the cache value stored by the other processor should be updated to the other processors. Okay. So how to tackle this one? So we have two solutions. The first one is snooping cache coherence, or the next one is directory-based cache coherence. Okay. So for the snooping cache coherence, when the core shared a bus, any signal transmitted on the bus can be seen by all the cores connected to the bus. So you can see here, core number 1, and then you have the cache here. Okay, you have interconnection to memory. So any signal sent here, updated, will be seen by all the cores connected to the bus. Okay, so when core 0 updated the copy of X stored in its cache, it also broadcasts this information across the bus. So if core 1 is snooping, just see. Okay, snooping means like just see whether there's some signal change. It will see that the X has been updated and it can mark its copy of X as invalid. So X in here can be marked as invalid because the core number 1 can snoop, okay, can pick whether core 0 has updated X value or not. Okay. Okay, so then the next one, it is not essential that the interconnect be a bus, need that it support broadcast from each processor to all the other processors. So you need to have a broadcast mechanism. Okay, you need to have the same information. Okay, and secondly, snooping work with both write through and write back cache. Okay. Okay, then the next solution is directory-based cache coherence. So in large networks, so you have multiple cores, for example, the broadcasts are expensive, and snooping cache coherence requires a broadcast every time a variable is updated. So snooping cache coherence is not scalable. So if you have multiple cores, you need to have a directory-based cache coherent protocol. Okay, so use a data structure called a directory. Okay, you have directory data structure that store the status of each cache line. So when a line is read into core 0 cache, the directory entry corresponding to that line will be updated, indicating that core 0 has a copy of the line. Okay, so you have core 0, okay, and the core 0, this is the core 1, for example, this is the cache, okay, and read from the memory, for example, X here. Okay, so the directory entry, so you have the another variable called directory corresponding to that line will be updated, indicating that core 0 has a copy of the line. Okay, when a variable is updated, the directory is consulted. So when X7, the directory is consulted, and the cache controller of the cores that have that variable cache line in their case are invalidated. So if core 1 also has X, so need to invalidate this one. And even the X here on the main memory should be invalidated because you have the new updated variable from the core number 0. Okay. So there will be substantial additional storage required for the directory, but when a cache variable is updated, only the core storing that variable need to be contacted. Okay, so you have multiple cores. Okay, only core number 1 need to be contacted. Okay, the others is can be free. Okay. Okay, the next one is fault sharing. So it is important to remember that CPU cache are implemented in hardware. So they operate on cache line, not individual variables. Remember that instead of storing one variable at one time, you can run 10 variables at a time, depend on the cache size. Okay, this can have this implication on the performance. Okay, so for example, we want to repeatedly call a function Fij and add the compute value into a vector. Okay, so for example, you have here, so you add the value and you call here, call this function. Okay, call function. Okay. So we can parallelize this by dividing the interaction in the outer loop among the cores. So we can, so this is cores, for example, and this is data. Okay, so we can, this is the outer loop. Okay, this is the outer loop. So we can divide this across the cores, for example. Okay, if we have core count cores, we might assign the first M of a core count iteration to the first core, then the next M of a core count iteration to the second core, and so on. So for example, if you have 4 cores and the data is 16, for example, you can first element to first core, second core, third core, and fourth core. Okay, so you can see if it's 16, then you can see this is 0 to 15, and then 16 to 31, and continue. Okay. Okay, so let's move on. Yeah, so if for example, we have 64 elements. Okay, in this case, or more elements. 16 times 4. Yeah, 64. Okay. Now suppose our memory system has two cores. And M equal to 8. Doubles are 8 bytes, and cache line are 64 bytes. Okay, so doubles precision requires 8 bytes, and cache line are 64 bytes. Mean you can catch 8 variables. Okay, and why not is stored in the beginning of cache line. So a cache line can store 8 doubles like this one. 8 doubles mean 8 variables of doubles, and Y takes one full cache line. Okay, so what happened when core 0 and core 1 simultaneously execute their code? Okay, since all of Y is stored in a single cache line, each time one of the cores execute the statement this one, okay, the line will be invalidated, and the next time the other core tries to execute this statement, it will have to fetch the updated line from memory. So it looks like Y1 is put on the cache, but it's always written by core 0, core 1, and other cores, so that when you have new when you write something, and then the memory will be invalidated. Okay, so the next core need to be updated line from the memory. So it looks like this in the cache, but still the which one is valid in the memory. So you need to read from memory. So means that you have the false sharings, mean you have the false what you call false impression that your Y, the variable Y is in the cache, but in fact it is on the memory. Okay. So if n is large, you would expect that a large percent of the assignment will access main memory. So in spite of the fact that core 0 and core 1 never access each other element of y. So this is called force sharing because the system is behaving as if the element of y being shared by the core by the fact it is not. Okay. But the force sharing does not cause incorrect result, only slow down the computation because it does not put in the cache. Okay. Yeah. So you can see here, can ruin the performance by causing many more memory access to memory than necessary. Okay. We can reduce it effect by using temporary or storage that is local to the thread, then copying the temporary storage to the shared storage. Okay. Okay, so yeah, so this is the summary, the shared memory versus. So which one to select between shared memory versus distributed memory? So why all MDCs are not shared memory is easier since most programmers find the concept of implicitly coordinating the work of the processor through shared data structures more appealing than explicitly sending the message. Remember, for shared memory, you are shared the memory. So if you have data in memory, for example, you can share it among the cores. Okay, but if you have distributed memory, then the data here in the one memory is different from data here in the other memory. So you need to send. Okay, and the PC number 2 need to receive. Okay, so the principal hardware issue is the cost of scaling the interconnect. Okay, as we add processor to a bus, the chance that there will be conflicts over access to the bus increase dramatically. So buses are suitable for system with only a few processor only, and as well the large crossbar are very expensive. Okay, and then distributed memory connects such as the hypercube and the toroidal mesh are relatively inexpensive, so it's cheap. Okay, so you can connect using hypercube connection. Remember the hypercube, 1, 2, and then like this. Okay, or toroidal mesh. Okay, you can have toroidal mesh, can across like this. Okay, and so on. So distributed memory systems are often better suited for problems requiring vast amount of data or computation. So all has pros and cons. Okay. So as the summary for this chapter, we have discussed the phone memory architecture. We have discussed process multitasking and threads and modification to the phone memory model because we have the bottlenecks. We have basic of caching, write through or write back. Cache mapping can be fully associative, direct map, and n-way set associative. Okay, and for another modification to phone model is virtual memory. Okay, we have swap, space, page table, and translation look aside buffer. Okay, and instruction level parallelism, also accessing different data using the same instruction, also modifications for the phone models, and we have also hardware multi-threading. Okay. The last one is the parallel hardware itself. Based on the Flynn taxonomy, we have SIMD system, MIMD system. We have discussed shared memory. Shared memory have UMA and NUMA. Okay, we have interconnection network, shared memory, bus and crossbar. Distributed memory, direct, it will be ring, toroidal mesh, and hypercube. Indirect will be crossbar and omega network. All has its own pros and cons. Okay, either you want the speed or you want to minimize the cost. Okay, so there's the two things. Okay, and then we have cache coherent issues, and then to solve that we have snooping. Okay, so this is only applicable for small number of cores, or we can have you have more number of cores, then you can use directory based, although it uses some memory to be used as the for the directory. Okay, directory variables. Okay, then we have shared memory and versus distributed memory. Okay, thank you very much. Okay, assalamualaikum warahmatullahi wabarakatuh.